sobie ozdobię jak ci pokój.
All right, so welcome to the second workshop today. It will be by Damian from Aleph 0, and he will be talking about client-side proving. So please welcome Damian.
Awesome, thank you. So even though this is a workshop, it will be quite conceptual, not very technical. So yeah, I will try to not go deep into these technical details and mostly talk about, things on a very high level. Okay. So I'm Damian. I'm in Aleph 0, and this will be about client-side proving. And so I'll essentially explain what this is and what are the challenges and how it differs from what we see most of all in the ZK space. Great. So let's start by maybe explaining from a high-level viewpoint what ZK snarks are about. So to have ZK snarks, you need to have a fixed computation. And this fixed computation is typically modeled as a relation, so a computer program which takes two inputs. It takes a statement input and a witness input. So normally the statement will be something public, witness will be something not necessarily public. We'll see in a moment. And a basic example of that would be to have a statement being some kind of a hash and a witness being the preimage. Okay? So the relation then is checking whether hashing this witness gives you the statement. And it's this kind of relations which are interesting because there is some kind of a secret hidden in the witness which is not easy to guess. Okay, so these are often the statements that are interesting. These are the relations which are interesting. All right? So based on such a relation, we then can define a ZK snark. So here's the setting. There are two parties. There is prover and there is the verifier. If you are thinking about blockchain applications, verifier is basically everyone. So everyone is the verifier. Everyone would like to be convinced that some kind of a statement is true. Okay? And there is this prover who generates a proof based on the statement and the witness. They generate a proof that this relation with arguments, the statement and the witness, evaluates to true. Okay? So this pi here is the proof, and the prover generates this proof and sends it to the verifier or posts it to the blockchain. This is the standard setting. So now once the verifier gets this proof pi, it will run this verification procedure. Here I call it ver. So the verification procedure takes s and pi. So you can go back to the example and think of s as this kind of a hash that we are looking for. And pi is a proof that this person, this prover, knows the preimage of the hash, right? So this is the definition of the snark. In ZK snark, the proof has this additional property that the verifier will not learn anything about about the witness, right? So even though they will learn that the prover knows the preimage, they will get no idea of what this preimage is. So that's the setting we are talking about. That's the building block that is used in many protocols. And what we normally care about, and what was actually the great achievement in the recent decade, I would say, is to make these snarks efficient, in the sense that generating the proof is not only polynomial time, but it's actually very fast. It's the efficiency is kind of not so far away from just evaluating the statement, evaluating the relation R. Okay, great. So this is the general setting. If you don't understand, it's fine. If you have seen it before, that's great. But yeah, we will just focus on the high level here. So now, how do we use these snarks? Why do we care about them? And I would say there are mainly two categories of applications, and especially if you are new to this space, you should put a thick line between them and just try to not mix them together, because this will confuse you otherwise. And especially if you are reading some marketing materials from different projects, yeah, you will get confused very easily. But this is how it is in reality. There are two directions of how snarks are used, and the one direction is to use snarks for scaling. So basically, you have some program which is compute intensive. So this is the relation R that we talked about. And there is this very powerful prover who runs this computation, creates a proof that this is the correct result, and it posts a proof for others to not need to run this computation again. Okay? So this is for scaling. This is to make things efficient, because the other parties, they don't really care about any secrets. They don't care about hiding anything. They just want to see a proof that some kind of probably heavy computation was done correctly. So this is the scaling application. And maybe the most interesting or most famous example are ZK rollups. And as you can see, I spelled ZK rollups with a quotation mark. So now you can see clearly why, because it's not about ZK, because ZK is zero knowledge. There are no secrets here. This name is not quite accurate because of that, but it's fine. This is how we call them, but that's good to know, good to be aware that this is not about zero knowledge, it's about scaling. Okay, it's about succinctness, the proofs, it's about very efficient verification of something which is time consuming. Okay, so this is the one direction. The second direction is completely different, and it's about privacy, because snarks, and in this case ZK snarks, give us this additional property of secrecy, of hiding the witness. And this is what we are using here. It is typically used in systems that offer some anonymity, like anonymous payments, like Zcash, where the user has some particular secret, some kind of a key, some kind of identity that they don't want to show to everyone. Okay, so now this is the client-side proving term that it comes here. This is the title of the workshop, actually. So we will be focusing on this privacy application today. So client-side proving, because the proof that is generated, the snark that is generated in this privacy direction is generated by an actual user, a user who holds some kind of secrets, right? And for the scaling application, it doesn't really matter who computes the proof. This will be typically some really powerful machine. This might be a cloud machine on AWS, which is basically the most expensive there is, because we just need one such machine to compute the proof, and then everyone just verifies the proof. And basically, we don't need to redo this computation. Just one server that can do it. Okay, so these are the two directions that we have in applying ZK snarks to actual products, to actual things in real life. Great. So what about the verifier? Because we kind of Talked about proving. That was server-side proving for scaling, client-side proving for privacy applications. So where does the verifier live? Normally, it lives on the blockchain. So you send a particular transaction which contains this proof, and there is a verifier implemented in a smart contract or implemented natively on the blockchain. And there are a couple of issues, technical issues here, which are related to what are the capabilities of the chain to actually deal with this verification. Verification normally uses some particular crypto primitives, uses some particular elliptic curve operations. They are not always supported. Like on EVM, what we have is this BN254 elliptic curve. This is pretty much the only curve that can be used for verifying the elliptic curve snarks. Even though people would like to use other curves because of security, because of other things. So that's why we see now the emergence of verification layers. So there are a couple of projects who try to kind of help with verification. There are issues with verification. You cannot really verify all kinds of snarks on chain. So they allow you to do that by delegating this verification kind of off-chain. Okay? So basically the way it works is you have some off-chain agents who wait for proofs to be posted on chain, and they attest that the proof is correct without the proof actually being verified directly on chain. There are many different mechanisms to do that, but this is essentially how these verification layers work. Of course, this is not for free in the sense that the verification layers allow you to kind of verify the proofs cheaper, meaning less gas consumed in a smart contract. But there are additional security assumptions that these attesters actually do everything correctly, they don't collude and stuff like that. So this is about the verifier. Now let's talk more about proving again. Actually, this talk is about proving. So from now on, we'll focus on that. And specifically, how would you use snarks? How would you apply them in a project? You would use one of the existing libraries, most likely. And there is some kind of let's say hierarchy of different kinds of software that you can use for snarks. And the hierarchy is based on how low level or how high level the library is. So from the left, you have the most low level libraries. And by the way, this list is not comprehensive. There are many awesome libraries missing, and yeah, I just didn't pay too much attention to list everything. But from the left, the most low level, where you can really be very close to the cryptography. So there are finite fields, there are arithmetic constraints, there are gates. So this is what you deal with in these libraries. That's how you specify your relation. It's quite low level, but it gives you a lot of control. And then the arrow on the bottom, it also tells you that kind of the higher level you go, the more overhead you pay for this convenience, in a sense. So on the left, Halo 2, ArcWorks, Circom, these are quite low-level libraries. Then there are some libraries like, it's not really a library, it's a language, Noir, which is domain-specific language in which you specify your relation. And then it compiles down to some lower level implementation. But obviously this compilation is done automatically, so you pay a little bit of overhead in efficiency. And then there are these ZK VMs, how many call them, like RISC-0, SP1, Jolt, and a couple of others, which allow you to essentially write a program in a high-level language. And in this case, it's Rust. And you just, and everything happens automatically. So it's compiled down to an algebraic representation, which can be used for snarks. So yeah, this is lowest level. You need to care about you need to care about concrete arithmetic constraints and gates and stuff like that. Then there is noir. You don't need to care about that a lot, but still you need to have some kind of understanding that there is this algebraic level below, because you have specific kinds of variables, like finite field variables and so on. And then there is Rust. You just don't care at all, but obviously you pay a higher price for that in terms of efficiency of the prover. Great. It's like writing programs in assembly, C, and Python probably, right? So you expect, if you are an assembly expert, then your program will be probably the most efficient. But maybe you shouldn't really start your adventure with assembly, but rather with Python. So that's a similar story. Great. So now this is something that people kind of are intuitively aware of, but they don't know the numbers. At least many people were shocked when they hear these concrete numbers. But it's actually good to really see them, and then you actually know which things are possible, which things are not, which things are possible to do now, which things are far away. So when you measure the difference between actually running the program, this relation that talk about, and generating the proof for this particular computation, then the overhead is actually 4 to 6 orders of magnitude. So 10,000 to 1 million times slower. Okay, so if you have a computation which takes, let's say, 1 second, generating a proof for it would take 1 day. Okay, and obviously this is a very general statement, and it depends a lot about what kind of statement it is, which proof system are you using, which library. So obviously there will be cases where it's faster. There will be also cases where it's slower. This is just an average. So you see that the overhead is actually huge. So that's why the ZK EVMs, ZK rollups are not so easy. So to prove the whole execution of the Ethereum virtual machine, which takes even a couple of milliseconds, well, you need to multiply this execution time by this number. And in particular, the computations in EVM, like Keccak hash functions and so on, are especially unpleasant for ZK snarks. So you are probably closer to this 10 to the 6th. So that's why this is a challenge, and that's why it's such a great achievement to actually have these ZK EVMs. Great. So now let's talk a little bit on how can we make it fast, actually, how can we make it practical. And first, let's talk about server-side proving. So things which don't require privacy, things which are done on powerful servers. So the first kind of idea is to basically use better computers. So if you run on your laptop or your MacBook, then you will get certain proving times. But then if you switch to better hardware, you will get better running times. It's quite obvious, but well, this is essentially done and pushed to the limits. Basically, the best possible machines on AWS are used in this ZK EVMs typically to generate the proofs. Then there are ideas to use parallelism. So generating a proof is a particular computation. It can be parallelized to some extent, not perfectly, but some parallelism is possible. It's not easy, and that's why this is not just an automatic optimization that everyone uses. Currently, this is done for some proof systems. People have done it for certain variants of Blanc, I guess. Graph 16 is proof systems. But still, it's not so obvious. I mean, there is lots of work to be done here to chop this computation into many parts, which can be combined together and allow us to make it faster. So this is possible, but it's not so easy, I would say. Then there is this idea to use specialized hardware, and yeah, there is lots of projects currently doing it. They are manufacturing all kinds of specialized hardware for proving snarks. And yeah, there are all kinds of ideas, from using FPGA, then to introducing specialized types of GPUs which are optimized for finite field arithmetics. There are companies producing ASICs for certain types of snarks. It's not easy because manufacturing hardware is a long process, and the standards that we don't really have standards for snarks because things are changing so fast. The progress is so fast that, you know, once the hardware is manufactured, then there are new ideas. A new snark proof system is better, and we need to redo everything. So that's why, even though this has a lot of potential, it's still, I would say, work in progress. And there is this idea of proving networks, which you have probably heard of. There is the Bonsai network from RISC-0, which is probably the most famous, but also there is proving network for SP1, if I remember correctly. There's quite a couple of them. And what you essentially do is, instead of generating the proof by yourself, you delegate this task to a specialized kind of network of provers. And why is the specialized network better than doing it by yourself? Well, you don't need to solve all these challenges, like with getting good hardware, maybe with optimizing, maybe with using GPUs and stuff like that. So yeah, these are essentially specialized products to help you generate proofs quickly. Great. So now the question is, can we do the same for privacy applications, for when the proof needs to be generated on the client side? And this is maybe not looking so good. Because there is this, first of all, there is this fundamental limitation that if we build products for end users, then we cannot really offer them desktop applications, because that's not something that happens in crypto. In crypto, if you launch a product, then you interact with this product either through your browser, so you have extensions in your browser, you have web apps, you connect typically you connect your wallet to the web app, and that's how you use it. So web browser is one important platform for launching crypto products, and there is mobile phones, where you have apps for crypto. Desktop is not really a thing because it's not convenient. It forces you to install a new application on your PC. And even though we would like it, because proving on desktop is much, much faster than proving in web browser, proving on mobile, we cannot really do that. So this is annoying. And what's even more annoying is that all these ideas that we analyzed before are not really possible for client-side proving. So when it comes to better hardware, well, if you are running a server for generating proofs, then you can just upgrade to a better server. But if we're shipping products to users who are expected to generate proofs on their devices, then we cannot just ask them, oh, buy a new phone or buy a new laptop, because, well, we cannot really do that. So we cannot really expect that this will happen, that everyone will upgrade their hardware. When it comes to parallelism, well, the only source of parallelism we can use is this coming from multiple cores on your laptop, on your phone. And well, this is obviously possible, but it's very limited. So people don't have too many cores on the laptops typically. If they use it mostly for web browsing, they are not users with powerful CPUs and so on. So we cannot really rely on that. Specialized hardware. Well, specialized hardware is applicable for this server-side proving because that's where you can install specialized hardware. It will not happen that specialized hardware is released today and tomorrow everyone has the hardware on their phone. This is not possible. If there is a specialized hardware released today, then people will have it on their phones in 10 years, right? So that's the cycle for hardware. It's very slow. And proving networks, this is actually interesting because, well, if you have a very limited device, why don't you just delegate the task of generating a proof to a proving network? This is the thing, right? So it's indeed a nice idea, but there is this open problem currently that we don't know how to do trustless delegation. So there is this user who wants to generate a snark. They hold a witness, but this witness has some secrets that the user doesn't want to reveal to others. So now, as you can see, the proof generation procedure takes as inputs the statement, obviously, but also the witness. So in order for a proving network to generate the proof, they would kind of need to know the witness, but we don't want to reveal the witness. So there needs to be we need to have some kind of a clever trick to maybe pre-compute a little bit of the proof, send it over to the proving network, and then do the rest, do the heavy work. This would be ideal, but so far we don't know how to do that. Okay? So this problem is actually very instance specific. Depending on what kind of proof are you, do you want to generate, the hiding of the witness might be easier or harder. There is this example in Zcash where the witness they have is essentially divided into two parts. Is some kind of a spending key, and I will call it privacy key. So what the user can do on their side, and it's very easy computationally, is generate a signature. This is just a few milliseconds. And then the rest of the proof of the snark, given this signature, can be delegated in a sense. So they can send over the privacy key to some other party along with the signature they generated on the device, and the other party will be able to generate the proof. So the issue here is obviously that the other party will then learn the privacy key the privacy key is actually responsible for privacy in Zcash. So the user will not compromise their assets because this is why there is a separate spending key, but it will compromise its privacy to this party it delegated the proving to. So I would say it's a nice direction because then you can at least choose who to trust, but it's not for free. You compromise some privacy. Good. But yeah, what we are looking for is a general kind of technique that will allow us to do that for any relation. Great. So yeah, it's very challenging to prove things on the client side. We don't have access to all these powerful ideas to speed up proving. So let me offer one concrete setup that we use at Aleph Zero to actually generate proofs on the client side, which we think is quite effective. There's some potential for optimizations. And yeah, it offers quite good proving time for what we use. We use a Halo 2 library. It's a low-level library, so we have lots of control, and we don't pay much overhead. And then we compile everything to WASM. So Halo 2 uses Rust. It's a Rust library, and then essentially compile to this cross-platform binary format, which we can run in the browser or mobile. So then, well, can we actually do some multi-threading for WASM? And it's tricky. One idea would be to use these web GPUs. This is kind of a standard. Maybe not really a standard, but something that might become a standard soon for using GPUs in web browsers. So, well, here you can see some kind of a diagram. Red means not supported, green means supported. And these are different browsers. These are different versions of the browsers. You can see that Chrome, Safari kind of support web GPUs. Firefox doesn't. There are all these little asterisks here, which I don't have here, but they say if you are on a particular operating system, you might need to manually enable it. So the conclusion from this is that web GPUs are not yet supported so well in general because, well, you cannot just expect that the user launches a web app and the web GPUs will be supported out of the box, because there are too many possible scenarios where it just doesn't work. So this is telling us that web GPUs are not yet a solution for multi-threading, and in particular for speeding up proof generation. So what we use instead is there is this Ryan library that allows you to do parallelism, multi-threading in Rust, and actually Halo 2 supports some kind of Ryan. So we essentially use Ryan and plug in web workers, which is some kind of a web standard to get parallelism, to get multi-threading. It's not so easy, so you would think that, well, yeah, you just put it together and it works. This is far from easy because there are no common standards between web browsers. There is lots of things breaking between versions. So doing multi-threading is possible. It's kind of stable, but, well, by no means it's easy. So now maybe to convince you that multi-threading is actually kind of necessary, is there is the benchmark which says that for a particular relation, generating a proof natively on CPU, this is what you would see on, let's say, on the server-side proving thing. It takes just 1.2 seconds, and if you go to WASM and run it in browser, well, it will take over 9 seconds. So there is like an 8 times overhead in proving. And it's really annoying because WASM, if you look for materials in WASM, it often tells you there is a max 2 or 3 times overhead in computing in WASM versus native, but it's just not the case for cryptography. Cryptography is much slower. So, well, if you manage to actually run with multi-threading, you do a couple of tricks, you do some optimization, you can bring it down to the kind of close to the native time on single-threaded. The 2 seconds is roughly what we can get for these particular benchmarks. By actually optimizing the circuits further, we can even get better times. But, well, it's still, whereas 1 second or 2 seconds on the user side is probably acceptable. Having 10 seconds or 20 seconds is, well, it's not ideal then. So really this constant optimizations are really important in client proving. And this is often what we need to rely on. So that's the state. Thank you.
Thank you, Damian. I think we can fit at most one question, so.
Hey, hi, great talk. I was actually thinking, I started building a mobile app which uses ZK-BOP in the background. The idea here was that to build an app where you can send someone money in a private manner, right? And the problem was the prover, obviously, right? When you want to, like on a mobile device, when you want to prove something, like if you have a very cheap device, you won't get anything, right? Or it would take very long or whatever. So yeah, like UX-wise, you could give the user an option to either decide to prove it on the phone or to prove it with the outside, like prover layer or network. But yeah, I was thinking, like, is it better to wait for devices to get better hardware in the future to do this stuff? Like, if you're thinking right now, AI is getting very popular, so devices, phones will get better hardware in the future. Like, can this be used for proving in the future?
Yeah. Regarding the first thing you mentioned, to give the user the option to either do it on their phone or delegate. So this is always very tempting to do, to give the user the option, but then guess which option the user will choose, to do things faster or slower, right? And no matter whether they have a more powerful device or not, they will just choose the option which is faster, right?
I mean, you can do that in the background without giving the user the option. Like if the user has a powerful device.
Yes, so doing things in the background is actually a very nice trick. It can be used on mobile. Unfortunately, it cannot be used in web browsers. There are like technical obstacles here. But I think for now, I think the idea of doing things in the background is quite good, I would say. This is something, I mean, let the user push the button, and it just tells you, well, things will continue in the background, you can do other things. And the user will say, okay, I will do other things. Maybe it's not super great UX, but I think it's something, and if we get privacy for that, well, I think it's worth it. I would say, the hardware, especially on mobile, is getting better and better. I think with enough optimization on the circuit level, on like on this low-level stuff, you can get good proving times on mobile. But yeah, obviously it's a lot of work.
Do you think AI hardware will help here? Could be used for that?
That's a good question. AI hardware is normally, it will probably be optimized for floating point operations, which might not be super useful here, but yeah, I'm not an expert, honestly. So I know people use GPUs for proving, and actually there is, yeah, lots of speed up you can get with GPUs. So if you can get speed ups with GPUs, then you should be able to get speed ups with AI hardware as well. So yeah, I mean, this is a possibility. The question is when, right? So when will the AI hardware modules will be available?
Do you think hardware improvements will come faster than this, the network, the proving network improvement in terms of privacy?
Yeah, proving network thing. I mean, for privacy, there is this obstacle for using proving networks that this trustless delegation problem is not solved yet.
Yeah, yeah.
Well, if we have that, I think proving networks will take over, because proving networks are easier to build. You just slap a server and this is a proving network, like nobody will care like what's inside, right? And if this server is fast, then it can prove things. But here, yeah, we need to kind of solve this problem of leaking secrets first. Yeah, thanks for the question.
Yep, thank you, Damian. And let's take a 10-minute break, and let's meet in 5-minute break. Right. Thanks.